Just add a little bit to my background. I started as a metallurgical engineer. That was my undergrad. So that was a lot of, you know, essentially understanding how iron and steel is made. And I liked the material science and the chemistry aspects of that, but was also very drawn towards economics and thinking about kind of demand and supply and uh, economic models. And I guess I learned at some point that um, materials and commodities are sort of fundamental to all the products we make and use across the world towards economic growth. We kind of define ages of history based on materials, right? Like the Bronze Age and the Iron Age and the Silicon Age or whatever. So I was very interested in sort of how materials enable economic growth and prosperity and also sustainability. And I learned about this interdisciplinary program at MIT called the Technology Policy Program. Sounds a little like it also has like people of all kinds of disciplines coming together. So it sounds a little similar to this graduate program. And that's why I learned that there is a whole field of research which sort of models the supply chain of materials and tries to figure out how to make those supply chains more sustainable, how to meet the needs of future generations, the material needs in a responsible way. And so since that master's program, I really enjoyed that research, stuck around to do a PhD, and now I'm a research scientist. And throughout that period of time doing research, it's been focused on understanding how demand and needs for materials will evolve in the future and how we can meet that demand in a responsible way. And I'll be talking much more about sort of the challenges in that space over this seminar and some of the models that can help inform both technology development and policy that can meet those needs while minimizing societal impact. So I'm just going to share my screen right now. And kind of the way what I've titled is Integrating Materials and Energy Analysis to Accelerate the Energy Transition. That's a little buzzwordy, and I think it'll become more concrete as I go along. But the idea is that we think a lot about how to make decisions about which energy technologies we should deploy, right? We think a lot about should we deploy solar or wind or geothermal in which locations, but often we don't think as much about what are the materials needed to make those technologies scale up and how do we invest in the supply chain of those materials to ensure that those technologies can actually get built and do not have some unintended consequences. I'll be talking a lot about how to think about the interaction between scaling up energy, new energy, renewable energy technologies, while thinking about where you need to develop material supply chains that enable those technologies. And I'm happy to take questions as I go. Like I prefer people to just like, I think because it's a big enough room, I'll probably just take pauses and ask for questions. Something burning, feel free to interrupt. So the first thing, just to kind of set the context, is that we really need to scale up materials production to meet the demand for the energy transition. So on the right here is the demand for four materials, cobalt, nickel, copper, and lithium, in a modeled net zero scenario. So some people have modeled the kind of technologies you need to deploy to have net zero emissions in 2050. And then they have calculated based on that, what is the demand growth for these four commodities. And you'll see that this demand growth is very large, right? So for some commodities like lithium, you expect like a 900% greater demand in 2050 compared to 2020. So there's this urgent need to build up the supply chain of materials and minerals to meet the need for these renewable energy technologies. At the same time, you want to build that supply while enabling supply chain security and availability of that supply, right? So typically the supply chains of these materials end up being very concentrated. So on the right here is the for lithium, nickel, cobalt, and manganese, the supply concentration of mining and materials processing. And you'll see that in all of these cases, a few countries dominate the supply chain. Uh, in mining, for example, for lithium, it's dominated largely in Australia. For nickel, it's Indonesia. For copper, it's in the for cobalt, it's in the Democratic Republic of Congo. And when it comes to like downstream processing of these materials, it's like majority dominated by China, right? What that means is that as you scale up the supply of these materials and these supply chains are so concentrated, you're also exposed to geopolitical disruptions, right? In a world where you really need to deploy these technologies and need to have access to these materials, the fact that the materials are concentrated in certain countries means you're exposed to risk that you will not have that material available when you need it. That could be risk from things like natural hazards and just disruptions that shut down these projects. There could be trade barriers that get set up into the future. So all these risks mean that while you need to scale up the production of material, you also want to ensure that the supply chain is diversified and not concentrated in such that so that you're exposed to essentially not having access to those materials. And finally, you also want to minimize the impact on various systems along where these mine sites are located, right? So the figure on the left is an artwork, which basically describes how much copper, which is that golden ball in the middle, you get from mining that whole area of land. So essentially you dig up like this whole area really deep to get that ball size of copper, because you typically have around 1% of copper in the geologic ore deposit, right? So there's a significant land impact to mining. Also, kind of analysis has been done that shows that most of these energy transition resources are located in regions with high water stress and water risk, and you need a lot of water to transport materials at mine sites. And also, most mine sites are located near indigenous communities, right? So 70% of resources are close within, I think, within like 10 kilometers of indigenous land. So at the same time, you have this multi-dimensional problem. You need to, for the renewable energy transition, you need to scale up the production of these materials, but you also want to make sure you've like done it in a way that is diversifying your supply sources and minimizing the environmental and social impacts from that. And that presents sort of this planning challenge of how do you balance these kind of competing considerations of local impacts, energy security, and the availability of low-cost materials that enable these technologies. And I'm going to talk to you about how models can help guide those plans and how you can make better decisions for what technologies to invest in and which regions to build these projects in, so that you balance these considerations. I'm going to pause there and take questions on sort of that context. This is going to be the first question in the first seminar, so someone's got to break the ice, right?
Doesn't look like there's questions, but maybe I'll ask.
Can I ask a stupid question?
Oh, no. Okay, yes. Yeah, no stupid questions.
Yeah.
Yeah.
What do you mean by water risk? Like,
yeah.
Not having enough water or concentration of water?
Yeah, so that's actually a really, really good question. It's very, I think in that, the paper was talking about water risk is defined by this water stress indicator, which is sort of the balance between current water consumption and then water availability in that region, in the different reservoirs. So it's kind of like this ratio of how much is already being consumed in that region and how much is available in the reservoir of that region. But actually, there is a lot of complexity that I have not gone into in how people measure water stress. And it's actually a pretty complicated task. Yep.
When you had said 70% of the resources are near indigenous lands, are they on the indigenous lands, or are you just like, what is near?
Near is like essentially you take a map of where these mineral deposits are located. You take a map of indigenous communities, you superimpose that, and if there is sort of an intersection of within 10 kilometers, then you say it's near. So it's near or on, right? So it's So if you take the boundary of an indigenous community, and if it's within the 10-kilometer outside that boundary, it's considered near. So if it's within that boundary, it's also considered near.
But none of them have started like actively mining in those areas, or this is just outside of that type of context, or these are just the resources that are available without mining already?
So these are resources, including the ones that are being mined already and the ones that are not being mined. Yeah. So there are, so it's both. And sort of the idea is it's a proxy for what will be mined in the future, or what might be mined in the future. So
I have a quick question. So in the slide that you showed with the materials requirement, one thing that I was wondering is kind of how much that takes into account the sort of dynamic nature of what we might need. So for example, like cobalt, I think that there was a larger expectation of that material, but then transitions away from that particular type of battery chemistry is a trend that we've seen recently. So I'm kind of curious about how you deal with that.
Yeah, absolutely. So I'll say that there's a lot of uncertainty about those projections, right? And kind of that actually makes this problem even harder because the demand is shifting so fast. So let's say this, and you'll see this in the case I'll present on nickel, because you're seeing the shifting in nickel away from nickel-based chemistries for batteries as well. The challenge is that mining companies have to plan out essentially 30 years into the future for their projects, right? So it takes around 10 years to develop and prospect and build a mine, and then they run for at least 20 years, which means that they need certainty that there will be a market for that product for in the next 20 to 30 years. Now, in the case that you just described, that people move away from certain chemistries like cobalt, there's a huge risk to making an investment in a mining property, and then that demand just goes away because people have discovered a new chemistry, right? So you had lithium-ion batteries, and then if they worry that in 15 years later people move away from lithium-ion, then that market completely crashes and goes away. And that means that either supply tends to get set up in greater risk-taking environments. So that's why a lot of I would say Indonesia has been pretty aggressive in building mineral supply for things like nickel. And in cases that supply is getting set up in risk-taking environments, they tend to ignore some of these other socio-economic considerations. And also what this means is often there's sort of this lag, right? Which means that because people are uncertain about whether demand will be there into the future, they won't invest in building new mining capacity until there is a shock and a spike in price. So you're exposed to sort of this imbalance between demand and supply, and that leads to high prices. And that high price means that things like EVs are more expensive, battery storage is more expensive, etc. So sort of there is a very interesting, like the uncertainty in demand, like what you described, means that people can't plan out well. And that means that you are exposed to imbalances between demand and supply, which hurts consumers.
Thanks.
Great. So what I'll go through now is this linking between energy systems and material supply chains. So kind of by show of hands, how many people here have heard of energy systems model? Oh, great. That's a large proportion of this room. That's awesome. So I'm sure you guys are all familiar, energy systems modeling essentially optimizes for a portfolio of energy technologies to meet energy demand, given some future constraints, right? So you're trying to minimize cost, you're trying to minimize emissions, you put some constraints, and the model predicts which combination of different energy technologies get built to meet that demand. But each of these these energy technologies, so let's say grid scale and battery energy storage, can choose a set of different battery chemistries, for example, between LFP, which is lithium iron phosphate, or NMC, which is nickel, manganese, cobalt, or sodium ion batteries. There are choices for which chemistries get deployed, And within those chemistries, there's sort of a range of materials that go into them. And for each of those materials, there is a different risk and different geologic distribution of where those materials are located, right? So typically, research in this field linking energy systems to those material supply chains happens in one of two directions. So either people start with the prediction from an energy systems model and estimate the environmental impact on the material supply chain. So that's the first set of research in this area, right? So what that looks like is people run this model. So these are the shared socio-economic pathways. This is a set of sort of commonly defined models for meeting like net zero targets. And what people would do is they would run that model. It would say, we need to deploy X amount of solar, Y amount of wind, X, Z amount of other technologies going into the future. Based on that, you would calculate how much material would be needed to build those technologies, and then estimate based on where those deposits are, what the water consumption might be for those materials. So like you'll say, we need a terawatt hour of batteries. Per kilowatt hour of batteries, I need, 100 kilograms of copper. Per kilogram of copper, I need, these many gallons of water. And therefore, this is how much water I will consume into the future in this scenario. Does that make sense? So that's the first set of work. You kind of start with how much energy is being deployed, or how much energy generation and storage is being deployed. You convert that to how much material you'll need, and you convert how much material you need to how much either water or emissions or pollution impact there is from per kilogram of that material. And that helps project out things like water consumption and environmental, like, GHG emissions in these supply chains. So that's the kind of research that takes sort of results from an energy systems model and estimates supply chain impacts going into the future. Similarly, here's another paper that estimates trade risks. So that's a different kind of impact. They take, again, this projection of net zero emission scenarios. They look at where mining deposits are located and talk about how trade risks might evolve at a country level as you transition from a fossil fuel-based economy to a renewable energy economy. And similarly, here's this other paper that takes kind of where mineral deposits are located and estimates things like how close they are to indigenous populations, etc. Right, so you kind of take results of these energy systems models, you estimate material demand in the future, and based on that demand and based on knowing where deposits are located, you say, okay, here is how water risk might evolve or water consumption might evolve. Things like that. So there's a whole set of models that goes in the direction from energy systems to supply chain, right? There's a second set of work that goes the other way, which is I want to estimate the impact on the energy system from a disruption in the supply chain, right? So what that does is it does something in, like, this is a paper from 2023 that they'll essentially have a surge in the price of materials, and they will evaluate the downstream impact of that on the deployment of clean energy technology. So in this case, they had these scenarios for a surge in the price of lithium, cobalt, and nickel. That was converted to a change in cost in battery, in NMC and LFP batteries. That changed the relative cost of EVs versus ICE EVs. And that then was used to estimate the overall carbon emissions from transportation, right? So here are the scenarios. So this is low, medium, and high price scenario for all these materials. And kind of what they found was the high price scenario for these materials had 28% larger emissions than the low price scenario. And that's because when you had high materials prices, it increased the price of electric vehicles, there's less EVs deployed, and that meant that emissions from transportations went up, right? So that's the kind of models that essentially you play with the price of a material, you estimate what happens to downstream products, and then the energy systems model or the transportation model tells you how much of that gets deployed. Similarly, this is a recent paper from earlier this year, which took this Reed's model. It's an energy system model in the US. And what it did is it had price shocks for various materials, so aluminum, chromium, cobalt, copper, and they estimated how that would change the deployment of different energy technologies. So what you'll see here is when there's a 100% price shock in aluminum, battery deployment went down 20%. And coal deployment was up 5% and gas was up 10%. And then PVs were down 20%, right? So when you had this shock in copper, which is this fourth column here, again, batteries went down around 20%, coal and gas was up. So you can see that shocks to the prices of materials impacted the portfolio of whether you had more coal and gas versus whether you had more renewables, right? So you kind of have a set, and all of this kind of these papers I'm pointing to are relatively recent. So you have this growing study of what's the impact of a supply chain disruption or an increase in materials prices on the energy system. And kind of the point I want to make is we need to get better at kind of going in both directions, right? Which is sort of that feedback between as you have, shortages in the supply of materials that impact how technologies get deployed. And that should change a demand forecast, to your point, Alan. And then that demand forecast should influence how the material supply chain gets built. So kind of what I'm going to talk through is sort of modeling approaches I've built, or just generally push people to think more of the interlinking between the demand for materials from these energy systems and the supply of materials and how that gets built up. So I'm going to pause there and take any questions.
For one of the first scenarios or graphs you showed us, you described like a low, medium, and high demand of the different types of materials examples. How did, I guess, how are you categorizing like low, medium, and high demand? Like, is it by a certain output, or because I kind of noticed that between the medium and the high demand, there's these big gaps in both.
Yeah, I think that's a great question. I think a lot of times the scenarios, so this is just to clarify, was low, medium, high price. So they weren't really, so they were just they were creating these price scenarios for lithium, cobalt, nickel, and manganese, but they weren't really talking about sort of why or how you would reach a low, medium, or high scenario. And often this is what you'll see. People will sort of assert a scenario and look at the impact of that, and often you won't get as much of a discussion of how or why that scenario might happen. So there is a huge role to play in kind of scenario development and how you do that better. I think the way they justified these scenarios was based on historic price ranges. So I think the high scenario was, if you look at sort of the historic price of lithium, it was the maximum price that you've seen in the last 10 or 15 years. And I think the medium was, I believe, 75th percentile, and the low was 50th percentile. And this is not low price, it's low increase in price. Does that make sense? Okay. They're not doing a low price scenario at all in this paper. They're just doing, you either have a moderate increase in price or a very strong increase in price. There could also very realistically be a decrease in price. And you should probably have like the flip side of this, which is if prices decrease, the deployment should become even faster. I don't think this paper did
that. Jason?
You mentioned there's a planning challenge. And so I'm kind of curious, based on your results, what are some recommendations you bring for how to invest to ensure security of the supply chain, or what are some policies that you think should change or be enacted?
So I'll talk much more about that, but to quickly just address that, I think there is, because of this planning challenge, you need much more coordination between end consumers and producers. What I mean by that is things like offtake agreements, right? So if I am an EV company, to be able to kind of go down to the suppliers, to the mine site or the smelter level, and give them some signal that there will be a demand in the next 5 to 10 years for that material, and to incentivize that investment. So that's one thing. Often what we found is that most of these mining projects are very capital cost intensive. So their ability to secure cheap financing impacts their costs a lot. So whether they get a loan at 15% interest or 5% interest is basically make or break for that project. And that's where either policy can come in to provide cheaper financing, like the loan programs office was there, who used to do for various energy projects in the US, or that's where sort of some of these offtake agreements help, right? So if I am a producer of nickel and I can go to the bank and say, here is Tesla, and they've guaranteed that they're going to buy my material for the next 10 years, I can get a cheaper loan because there's lower risk, right? So these are some strategies that can help, mitigate some of that uncertainty in the planning. So if you look at the most recent rare earths MP materials, so what happened 2 or 3 months ago is the Department of Defense invested, I think, $1 billion in a rare earth magnet producing project called MP Materials. And essentially what they did is completely de-risked it, right? They said, we are guaranteeing a price minimum, and if you are not able to sell at that price, we will pay you, right? So what the Department of Defense did is said, we really need rare earths for magnets for defense applications. So we're going to guarantee a minimum price to MP Materials, and also bought equity in that project. And that ensured that, and that meant that I think the private financing came in. It also, I think Apple co-invested, right? So what that did was create sort of this incentive where they're completely de-risked from these future volatility in prices. So in very strategic industries, there is probably some value in the end consumer, like the Department of Defense, or it could be an EV manufacturer, it could be a power, like a utility, right? Going in and providing that certainty or that signal to upstream producers. Yep. So, so the next part of this presentation is going to focus on economic models I have built that model, like in a dynamic way, how the supply chain for these materials get built up in response to changing demand, and kind of incorporates that feedback between prices and demand in, like, within the modeling framework itself. So the first thing to say is, like, we need to model both the demand for materials and the supply of materials into the future and understand how these balance in real market. For the demand side, there's sort of three things that lead to the demand for new mines or mining projects. The first is just demand growth from technologies, right? So you need more EVs, you need more energy storage, you need more solar power, and this is where your energy systems model output feeds in. So there's some growth in demand for materials based on the deployment of these technologies. But more importantly, there's also some substitution, right? So as prices of nickel go up, people substitute from nickel-based chemistries to lithium-based chemistry. So demand should be a function of that price of the material and not just something you assert as this is the demand. There is a recycling rate. So as you have improvements in recycling, you need less mining projects to be built. So that reduces the demand for minerals, like primary mining. And then there's some losses every year. So every year, the quality of a deposit goes down, because typically people mine the highest quality deposit first. And then as you go deeper and deeper into the earth, the quality gets worse and worse. So you need to mine more and more to get the same amount of it, right? So based on that, each year there is some amount of mining capacity that you need to open to meet demand. On the supply side, there are mineral resources. So these are deposits that we have found in the ground, but we haven't really exploited yet, which get converted to what is called incentive mines or incentive projects. So these are people will go in and go to a mineral deposit and conduct what is called a feasibility study. So they will buy that land and they will do geologic sampling, they will do techno-economic modeling to do a feasibility of what would it cost us to build a mining project in this area. And they will use that sort of feasibility study to go and get investment. And that takes around 3 to 5 years to do the whole feasibility study process. Then based on the feasibility of that project, they will make a decision on whether to open that mine or not. Right? They'll get investment from investors and they will make an opening decision. And what happens is that the decision on whether to open mines is informed by price. Right? So the decision, the feasibility is a function of price. If prices of materials or the projected price of materials is high, you have more mines making that opening decision. If the projected prices are low, fewer mining projects make that opening decision. And that price also feeds back into the demand, right? So price influences both the decision to open supply and the decision and how demand evolves into the future. And then the imbalance between demand and supply influences price going forward. So kind of the goal of this modeling is to build that feedback loop between the gap of demand and supply should influence price, then price should influence demand in the next period for materials, and also influence the decision of where supply gets built. So that's kind of the framework of the modeling that's trying to bring together that demand and supply side into one like interactive model. So I'm going to focus on the supply side first. So how do you even predict supply into the future, right? And how do you even estimate which supply will come online in the next 20 years? So the first thing to say is that there's a lot of data on geologic deposits. So this is a map from the US Geologic Survey, and they do a bunch of prospecting, different mining companies do a bunch of prospecting, and they report estimates of how much reserve or resource there is for each material in the ground. And that's one set of data we have. So we know how much material there is in the ground in most parts of the world. The other thing we know is we know the cost structure of current mining projects. So what you see here on the y-axis is the cost of different mining projects in dollars per pound. And on the x-axis is the cumulative production, where each bar is a mining project. So kind of order them from the cheapest mining project onwards to the most expensive mining project. The width of the bar is the capacity, and the height is the cost. This is very similar to a power dispatch curve, if you're familiar to that, where you have sort of power generation on the x-axis and sort of the cost of generating power on the y-axis. And the idea is that, the cheapest project will always operate, and the expensive projects will operate only if there is demand. But for existing mining projects or for mining projects that are very late in their development stage, you have sort of data on their cost structure. So you understand their capital costs, their operating costs, how much of that is electricity, fuel. So that's this other data set that we have on mining projects. So what we essentially do is build statistical models that fill in based on where the deposits are located and what you know about the quality of that deposit. You estimate the cost and quantity of production at those different projects. So you know that, let's say a project in Nevada has a very high ore grade or a very high proportion of copper as in the ground. And you have a regression model that tells you as a proportion of the ore grade, what's the cost, right? So typically, the higher the ore grade is, the lower amount of energy you need to put in to take away the copper from that rock. So you can build statistical models that are basically regression models that estimate these costs as a function of those geologic characteristics like their ore grade. Also, there's really you can map based on the size of the reserve, what the annual production tends to be. So typically there's a pretty linear mapping between reserve size and annual production. And you can use data on these geologic deposits to at least initial, and because you know which parts of the world they're located in, and you know labor costs in different parts of the world, and you know energy costs in different parts of the world, you can come up with an estimate of what the potential cost of a future project in a particular part of the world would be, right? So you had this supply curve on the left, which is currently operating projects. And then based on the ore grade and the location of the world, you come up with an estimate for all the other deposits that aren't being explored yet, what the cost might be in the future. What I will say here right off the bat is there's a lot of uncertainty, right? Like costs change over time. You know, as you develop a project, you might realize your ore is better or worse than you expected. This is sort of the best we know right now of what the cost might be, but you have to do a bunch of scenarios of how these costs might evolve. But the idea is to build this sort of estimate of long run availability and cost. So the dark purple here is currently operating projects, and all these lighter colored bars are projects that might come online if demand goes up into the future. And the height is the cost of those projects. And I know Pablo Bush, who was a graduate at UC Davis, recently published a paper kind of building these long-term availability curves for lithium, right? So there is, you know, you can look at that paper to, and it's really well done work on predicting sort of long-run availability. So that's the first step, which is like, how do we even know how much supply there is in the world and what the cost of that supply might be in the future? Yes, I saw a hand raised.
Making this estimate, are you also like accounting for the transportation to the processing like facility in this cost availability? Like even just infrastructure upgrades that might be necessary in that part of the world to get the raw mined product to the processing plant?
It's a good question, not explicitly. So what I mean by that is, typically within the cost, we're adding a treatment and refining charge, which basically is like the historic average of what the transportation and refining costs are on top of the mining cost. But it's not explicitly modeled in terms of where that refining capacity is and what the transportation cost to the refining facility. So the refining is definitely treated as like, oh, we assume that you could set up refining anywhere, and there is a particular average cost that you put for refining. But it's not, but you're right, that ideally you'd also want to have this level of geographic detail on the refining side also. But in this case, we kind of assume that you could build a refining plant anywhere, but you can't build a mine site anywhere. You have to build a mine site where the deposit is.
Right. Okay.
Yeah.
I have a question as well.
Yep.
So you mentioned the sort of factors that go into that, the cost curve, for example, these materials extraction cost curves, like, you know, ore concentration or whatever. How much does something like tariffs play into that? Is it maybe like a negligible effect, or do you think there's a significant effect on that cost curve?
Right now, there's a significant effect on the cost curve. Yeah, so you could take this model setup and then just go in and say that I'm going to add different levels of tariffs or subsidies for different regions and modify that cost curve. The one I'm showing right now, we assume none of that. We assume that the costs are purely based on geology and sort of geographic factors of energy cost and labor cost, but not sort of modifying that based on tax.
Do you think it would make like if that was added, do you think that would make a significant impact, or do you think it would be maybe close to negligible, or is that just outside the scope of your?
It's outside the scope of this work that I'm presenting, in the sense that this work is still in that idealistic regime where you assume that the demand and supply globally balances, right? But what you're describing is if you had things like tariffs, you'd have to account for the fact that for the demand in North America to be met, the cost of getting something from North America is very different from the cost of getting something from China or other parts of the world. So there, the model cannot just assume that demand and supply is met globally. You have to have a separate demand supply balancing for North America and for, let's say, other parts of the world. And then the supply curve will look very different for North America or for other regions. Does that make sense? Because you have to adjust that supply curve based on the tariffs. Awesome. So I'm going to kind of move forward. This is like a GIF, which I'll take a few seconds to explain. But on the left, what's happening is the black line is the demand curve for nickel. So we've taken a demand scenario. I think it was the IEA's net zero scenario, applied a demand elasticity based on other people's analyses. So people have analyzed how nickel demand changes based on change in nickel price. And so that creates this demand curve, which is the black line that's kind of in this direction. What's happening over time is that the demand curve is moving to the right because demand is increasing. As that demand increases and the demand curve moves to the right, the model is making decisions of opening more mine sites to meet demand. And that's why you see these green supply bars increase in width as the demand is going up. And what's happening on the right is you're kind of seeing the equilibrium between the demand and supply is leading to changes in price. And what's kind of happening in the background is every period as that price is changing, it is changing the demand because of that elasticity, but it's also changing the decision of the supplier of whether or not to open a project. So kind of these things are happening together in an endogenous way, where demand goes up in each period based on this demand curve. Based on the gap between demand and supply, there's a price that's formed. That price informs how much supply comes online and also informs how much demand changes in the period after that. And the results you'll see are kind of based on that equilibrium that gets created between the demand, supply, and price. Yep. Sorry, I can't hear.
Maybe stupid question, but is inflation accounted for all in this prediction, or in terms of the dollar itself?
It takes real costs and real prices. So we just assume these are inflation adjusted.
Okay.
So the cost on the mine side does not increase because of inflation either.
Right.
And so you assume, so this is like price at 2020 USD and cost at 2020 USD, right?
Okay, that makes sense.
So, yeah. And the other thing I'll say is for each of these projects, based on where they're located in the world and the kind of deposit that exists, you also can estimate the environmental impact in that region. So for example, the three ways, and I'll talk a little more in detail about the nickel case, to make nickel, so the three different kinds of deposits for nickel. And based on the kind of project, the emissions impact is very different. So sulfide deposits, the processing of that requires much lower emissions than laterite or like converting nickel pig iron deposits. And Indonesia has a lot of these pig iron conversion and leaching projects, while Russia and Australia have a lot of sulfide mines. So based on where the mine is coming online, you also have a changing environmental impact, right? So there is this interaction between what supply comes online and how the environmental impact sort of evolves over time based on that. So I'm going to kind of dive into that nickel example to kind of make it real into how you can plan better for this changing demand and supply. The first thing to say is that there's a lot of interesting things happening in the nickel supply chain. So what's happened over the last 10 years, 15 years essentially, is that Indonesia has gone and become from around 10% of global supply to 50% of global supply for nickel within 10 years. And a lot of these projects are Chinese-owned projects, and they've essentially made it a huge priority to grow nickel production in Indonesia because they have a large amount of nickel deposits. Now, I won't go into all the sort of like why some deposits have a larger impact than others. What you really need to know is there are three ways to make nickel. There are two kinds of deposits. The sulfide deposits, that's the one I was saying is predominantly present in Russia and Australia and Canada. And there are lateritic deposits. These are present a lot in Papua New Guinea and Indonesia. Now, of the laterite deposits, there are two types. And based on the type of deposit they are, you have to either do smelting, which requires a lot of energy to purify the saprolite deposits, or leaching, which requires a lot of acids to purify the nickel. And so if you look at kind of the emissions intensity of these three pathways, they vary significantly. So sulfide smelting requires emits around 10 tons of CO2 per ton of nickel. Laterite leaching is between 20 to 50, and then laterite smelting is between 60 to 120. And based on where that project is located, or based on the geologic deposit, you kind of know which processing pathway it will undergo, right? So you can estimate that. And on the flip side, it's very easy to set up a smelting plant. There's a low capex required, but it takes many years to build like a sulfide project because there's very few new deposits of that available. So most of the deposits are already being extracted, while there's actually a lot of available laterite deposits that are not being extracted. But you can bring online a lot of these high emissions projects really fast. But if you want to bring online these low emissions projects, it'll probably take you many years. So there's this very interesting trade-off between how fast you can grow supply and the environmental impact of that supply. And this is sort of talking similarly through other impact metrics. So you'll see a similar story in terms of water use, acidification potential, PM 2.5 as well. So we run this nickel model. We take that sort of modeling approach with data on nickel and run it in this net zero IEA scenario. And what you'll see is that while in 2024, a lot of the projects sort of split between, so majority of supply was this low emission sulfide smelting route. As the demand goes up really fast, most of the projects that open up in the next 10, 15 years are these high emissions laterite smelting projects, right? Because you really need to grow demand. Demand is very strong. You need to grow supply really fast. And that means that a lot of these high emission smelting projects come online. And what that means is that supply chain emissions from nickel go from around 30 kilograms of CO2 per kilogram of nickel to 70. Right, so you're doubling the supply chain, like the energy intensity of making nickel, because the kind of projects that are coming online to meet that demand are these high emissions projects. Right, and that's in the baseline scenario with no carbon tax, no prioritization based on emissions. It's just the lowest cost scenario. So you're just prioritizing the lowest cost projects with no carbon tax. And what happens in that scenario is that these sort of cheaper, easier to build projects in Indonesia come online, and that leads to this increase in emissions. So the question is, how can we meet that demand without having this supply chain GHG impact, for example? I sort of teed that up. You can put a carbon tax. And what happens is when you put a carbon tax of $100 per ton, it makes the supply much more expensive. And you'll see that there's this huge gap of demand and supply that opens up. What that essentially, and this is demand in the baseline. What that means is that prices of nickel go up, and supply. Let me simplify that story. Because you added a carbon tax, all these red projects became really expensive and did not open. Because those projects did not open, prices of nickel went up, and that demand, which was originally this black dotted line, went down. So the consumption of nickel did not meet what was originally projected by the IEA for the demand of nickel. So you had this, you saved sort of, so your emissions in the supply chain of nickel went down, but at the same time, you could not meet all of that nickel demand because you increased the cost of nickel production. So what that means is that battery prices went up. I know that I did not do a good job of explaining this, so I would like people to ask me questions.
I have a quick
question about the price projection again. How do you account for deposits that have a lot of different co-products too, like copper, cobalt, and others? Like how do you
Yep.
put that in the price? And also if the prices of those products change over time.
Yeah. In this case, we assume that you get the same, you get like the price of the co-products are fixed. So you get some co-product subsidy essentially on the cost of that project.
Okay.
With the nickel sulfide smelting, are
Yeah.
you problems with acid rain in those regions? Like, would that also be like a natural barrier to bringing those online?
Yes, so there is a project, there is a problem with sort of sulfur dioxide emissions in those regions. And then you need to have like really good flue gas, like desulfurization, scrubbers, wet scrubbers attached to this project. I think there are like, at least in like, for example, Canada and Australia, which has a lot of the sulfide deposits, there are very strong regulations around SOx emissions, so SOx emissions. So you have to basically have very strong scrubbers to ensure that you don't have acid rain impacts.
They're successful. Okay, thanks.
But yeah, to the extent that how I haven't looked at how successful those are, or looked at that regulation in more detail.
Yeah, I imagine it can depend on the country.
Yeah.
Strict regulations being so. Thanks.
Yep. Yeah. So essentially, what I'm trying to say here is that when you restrict something on the supply, so you say I'm not going to allow the dirty projects to open, you take a hit on the demand, right? You essentially have to reduce the amount of nickel-based batteries you're deploying, right? And this is assuming a particular substitution to LFP. And you see that happen here. So on the left, you have NMC 811 battery costs. So if you allowed all the lowest cost supply to come online, and there's some technology learning rate on these battery costs, the costs go from $80 per kilowatt hour to around 60. But once you restrict the supply of nickel based, or you increase the cost of the supply of nickel, the battery costs go up. Now it's sort of up for debate whether that's a good or a bad thing, right? On the one hand, you sort of mitigate some of these local impacts, but on the other hand, batteries are more expensive. And sort of the model can sort of present that trade-off, but then that's sort of where policymaking comes in to evaluate where you want to live within that trade. So what I'll kind of, another way to present this is battery cost is on the y-axis here, and the battery carbon footprint is on the x-axis here. And when you do a least cost optimization, you have a larger carbon footprint of the battery, but you have a lower cost. If you add a carbon tax on the nickel supply chain, the battery cost goes up or the carbon footprint goes down. What you could do is you could then say, what if I reduce some of that demand for NMC because I had a faster projection substitution to LFP, right? So what if I made LFP cheaper and made more people substitute away from NMC battery, nickel-based chemistries to lithium-based chemistries on top of the carbon tax? What that would do is essentially, because the demand for nickel went down, the prices would go back down and your battery costs would go down as well. So you can use this sort of interactive modeling to investigate a range of scenarios of what ifs in terms of substitution of chemistries, what ifs in terms of regulations, and try to identify strategies based on that. And what I mean by accelerated investment here is I reduce the timeline it takes to open a new project. What that meant is supply could come online faster and the supply-demand gap was reduced, so prices went down. So the point of all of this is to say building these economic models that link these supply curves for minerals with demand for minerals from the energy transition can help investigate a range of scenarios, such as the impact of supply disruptions on things like EV sales and on jobs, on things like what is the value of increasing recycling? Because if you increase recycling, the demand for mining goes down, and that could have a significant consequence on these upstream environmental impacts. And also, what is the value of things like innovation in mineral processing? So if you could reduce the cost of a bunch of these supply chains, what is the impact of that downstream on the prices of materials and the prices of products that use those materials. So, and I'm kind of wrapping up here. Another example of that is this work I did in collaboration with colleagues at CMU. They have this transportation systems model where you put in the cost of a battery, and that predicts and they have a technology choice model. Essentially, it says, would consumers buy an electric vehicle or a conventional ICEV based on what the price of that vehicle is? So what I did is I developed these price scenarios for disruptions in the supply chain. So for example, one of the disruptions was if China restricts the export of lithium, that increases the prices of lithium, right? And that meant that the costs of cars went up by around $2,000. And that led to 720,000 consumers in the US not buying EVs and BEV sales going down by 10%, right? So you can sort of, by linking some of these energy systems models or transportation systems models with models of supply chains, you can do these kinds of analyses, right? So the next one was, if there was a natural disaster, which meant supply of cobalt from the DRC was limited, prices of cobalt went up, and that led to $1,000 to $2,000 increase in the cost of cars. And you can kind of investigate what the downstream impact of these things are, and also then go in and play with what would happen if I increased the supply of materials by 100 kilotons, right? So what if I had a strategic reserve of 100 kilotons of lithium, and when that disruption happened, I could tap from that strategic reserve? That would reduce the impact of that disruption significantly. Similarly, if I had a larger adoption of LFP, so lithium iron phosphate batteries instead of NMC, I would not be exposed to cobalt price disruptions. So kind of integrating some of the supply chain analysis with these models of energy system transportation systems is just a very rich area of research, because you can really inform policymakers and inform strategies for how to mitigate against these disruptions and how to ensure that you mitigate against some of these environmental consequences. I know we're sort of at time for the kind of, well, I want to have more for discussions. I'm going to stop here. I'm going to skip this last case study, just kind of present these final thoughts of how we really need to think about the interaction between the supply chain and the demand, and this sort of strategic planning can be informed by research and by these models that link those pieces together. And in doing that, I think it's very important to interact with both policymakers and industry. So what I mean by that is, throughout the process of building this model, I've learned a lot by just like picking up the phone and trying to schedule a chat with people at mining companies, people at these battery companies, and ask them about how do they make substitution decisions. Ask them about how do they make investment decisions and what sort of is preventing them from investing in projects, things like that. You learn a lot by sort of engaging and like talking to people in industry. So when I started doing my PhD, I was trying to build these models in like sort of just, by myself. And I've learned over time that you can really speed up the utility of the work you do by trying to interact with people who are actually developing projects, who are actually deploying and making these sort of, strategic decisions. And people tend to be really willing to talk to PhD students, right? Because often people like to try to help someone who's just genuinely very curious and who's genuinely just trying to learn and, help inform some of these decisions. So what I'll say is that a lot of this modeling can be informed by, because things like cost data, etc., it can get outdated really fast. And that's why you need industry to kind of come in and tell you, actually costs have progressed a lot since the last paper that came out 5 years ago. And these costs have gone down significantly. So kind of talking to industry is really useful. Great, so I'm gonna stop there, and I would love to open up for questions and answer any questions, both on the problems and like sort of the research area. Thanks.
is it possible that by implementing say like a carbon tax, that countries will simply move to suppliers that your tax can't reach?
It is possible. Yes. It's and I think sort of the mechanism, like, and that gets into how well can you implement these policies, right? But yeah, I think that, and that's another case where like sort of then traceability becomes very important. So your ability to tell where did, and actually that's really hard to do. So the first research project I did was working with Ford, and they came to us and asked us, we need you to tell us how much material we are consuming in our cars. I'm like, shouldn't you know how much material you're consuming in your cars? And the answer is actually that was really complicated because their supply, so they have this huge database of 20 suppliers who are providing them various parts, and they all have different materials compositions, and all suppliers report different things. And in some cases, they report some things well, and some cases they don't report some things well. And if they needed someone to kind of take all that data, process it, and estimate, fill in the gaps in the data and estimate that. But actually, the point was the reason they need the academic step in, it's actually a really complicated task for them to track their supply chain. So I think there has been over the last 5-6 years a lot of traceability action. But I think to your point, the only way you'd be able to enforce that is if you had traceability. So if you knew exactly which mine site or which smelter your mineral was coming from, like, whether it was like fair, like kind of a fair trade coffee or whatever, right? But that doesn't really exist. The EU has the EU battery passport regulation. So that is one example of regulation that's trying to force people to report where the material is coming from. And that can ensure some of this, like you can then enforce some of these regulations, right?
Thank you.
Yep.
How do these sort of models account for so like for example with your battery case study, one of the big things that you were talking about was increased adoption of like LFP batteries and EVs. So what that means is like a transition from nickel usage to like lithium batteries, but that would cause significant shifts in the lithium supply chain, right? So how do you like account for that sort of like cross material effect?
Yeah, that's great. I think that is the goal. That's a great PhD project if you would like to do that. In that, like, yeah, I think that so there's sort of it is true. Firstly, I'll say that like both nickel, NMC, and LFP use the same model lithium, but I think they use more phosphorus, for example, in LFP batteries than NMC batteries. And you're right that here the scoping was the nickel supply chain, and I treated LFP as this external thing. But there's also that feedback of what you said, which is as you reduce nickel to LFP, or as this model predicts, or people substitute away from nickel, I should have a separate phosphorus supply chain model that links to that model and then does that. As you can see, it starts getting complicated really fast, right? Because then you're like, oh, but if both phosphorus and nickel go up, people move away from lithium batteries to sodium batteries. And then you can say, oh, but people move away from batteries altogether and go to geothermal, right? Or something else. So obviously this sort of you can have this explosion of complexity, in which case, at some point, everything is linked in the world is linked to everything else, and you can't model everything. So some of the choices you have to make is where you're going to draw that boundary. But that specific example is a good one. That, yeah, especially if you're talking about a substitution between nickel-based chemistries and non-nickel chemistries, you should look at sort of the downstream implication of substitution on phosphorus supply chains or some of these other supply chains.
Any other questions?
Yeah, I have one question. So when I will also work on copper and cobalt. So when I look at these demand projections, I usually think like either way, like the demand will increase a lot, and with ore grade decline and all these things, like they have like exploding like environmental impacts in the end. So basically, what I always think is like, wouldn't it be the best to try to reduce battery sizes? So I was wondering if you have ever done any work on like maybe looking at impacts of like incentives linked to battery sizes on these supply chains.
Mhm.
Anything done on that?
Yeah, I can share a paper with you later on. It's like we did this sort of bottom-up model where each automaker had like a budget, and if the price of materials went up, they could do various things such as reduce the sizes of the batteries, right? And then they kind of make, and sort of it's a decision model that the automaker has. But yeah, absolutely. I mean, and then like if you want to take that a step further, people should stop driving cars, right? Like,
Sorry,
and
yeah.
like, so there's also there is definitely like a large range of things you can do in terms of reducing demand. And to kind of Pablo's work, and also the work that I've done, there's heavy sort of non-linearities in environmental impact. What I mean by that is, like you saw with that nickel case, right? There are some really dirty projects, and there is a bunch of projects that are not as dirty. And if you can shave off that sort of that additional demand, you could get a significant reduction in the environmental impact. Think of like coal plants, right? Like in the energy system analogy. If you could build some additional battery storage, you actually reduce the need for coal plants, and that has a significant impact on your overall grid emissions. So similarly, if you could take off the most dirty mineral processing projects by either reducing demand by using smaller batteries or increasing recycling, there's this non-linearity, I think, in terms of the impact, where a 10% reduction in demand can have like a 40% reduction in environmental impact. I think as in terms of strategic planning, identifying those non-linearities is really useful, right? And communicating the value of that. So saying to policymakers that, if we could increase recycling, it's not just that we recycle the material, but we avoid all of these consequences. The ability to be able to say that and communicate that is really important. And I don't think we typically say, the way recycling is typically treated is, oh, if we recycle 10%, the average emissions go down by 10%. Or you take the average amount of, you take the difference between the emissions from recycling and emissions from mining, and you say if you recycle more, the average goes down. But what I'm trying to suggest is the impact is probably larger than that, because you're not reducing the average, you're reducing the marginal project that would have had a large impact. And sort of understanding what that marginal project is requires sort of this economic approach.
Thank you. Dave, you wanted to round us out with the last question?
Sure, I just wanted to know if you had modeled, I saw that water was one of the key indicators that you initially put on your graph. I was wondering if you also modeled it in terms of about like the amount of actual diesel or fuel that is required to extract the material from the ground, as opposed to just the greenhouse gas emission from the mining process, just in terms of like the price of the fuel versus the cost of the actual refined product after mining.
Yeah, so I think so that GHG number was sort of a combination of electricity and diesel. So there's some estimates of how much diesel is used on the mine site and then how much electricity is used. And there's sort of the sum of that impact was the emissions impact. What I'll say in general is, despite nickel is actually a unique case where some of these projects have really large GHG emissions. But in general for mining, like things like copper, things like lithium, we're not as worried about the GHG impact. It's typically things like water and land use and sort of community rights that are the bigger impacts. Because let's put it this way, you're still better off using a battery instead of an ICEV, even if your emissions from the mining were slightly high. Does that make sense? But some of the things like water impacts are harder to quantify because it's so hyper local, right? Because how do you balance the fact that there is slightly lower CO2 emissions in the world, but one region of the world now is starved out of water? You can't really. It's very tough to do that, right? You can't. Or so you want to be able to be very thoughtful about that. The one thing that just from talking to mining companies and industry is water tends to be the thing that they're most concerned about, I guess. Like that's the impact that they're trying to reduce. That is they can significantly change sort of reservoirs and water profiles of regions. And somehow a lot of lithium is in very arid regions, like it's in Nevada and it's in Chile and it's in like just I don't know if there's just like something geologically why that is the case, but there is, if you talk to local communities as well, water availability tends to be one of the biggest stress points for social acceptance of these projects. So if there are approaches from a research point of view, or just like if people can advance the thinking on how to think about water consumption, the trade-offs of like how to reduce water consumption in mine sites, how can we, there's a lot of value in them.
That makes sense.
All right, so everyone please join me in thanking Dr. Bhuwalka.
Thanks for having me.
Yeah, and I just want to say thank you again, that this was a fantastic presentation. And as you can see, all the questions, I think, pretty interesting for a lot of it, so thank you.
Okay. Well, yeah, hope you guys enjoy all the rest of the seminar as well. And sorry I couldn't be there in person. It was great to present. Thank you.